Let's elucidate the quantum counting algorithm. Previously, we adapted the phase estimation procedure to construct the quantum order finding algorithm, which is a subroutine of Shor's factoring algorithm. In this video, we're going to combine ideas from the phase estimation procedure with ideas from the quantum search algorithm. This will allow us to construct the quantum counting algorithm. We will explore the quantum counting algorithm with the help of this diagram. First, let's zoom in to the top of the diagram. Here we can see some useful definitions. Consider a set which contains all of the targets of search that are encoded in the oracle omega. Big T denotes this set. Little t denotes an element of big T. So these little t's are the targets of search, and they are labeled by L-bit strings, which are binary representations of integers. This set big T is a subset of the integers mod 2 to the L. And the total count C is defined as the cardinality of the set big T. The cardinality of a set is the number of elements in that set. So the cardinality of the set big T is the number of these little t's that are inside of big T. And each of those little t's correspond to a target of search. So if we count all of the targets of search that are encoded in the oracle omega, we're going to get the total count C. And we want this value of C to be less than 2 to the L minus 1. 2 to the L minus 1 is 1/2 of 2 to the L. So this inequality is a condition that we require for the total count C. These ideas come from the quantum search algorithm. And we're going to combine them with ideas from phase estimation to construct the quantum counting algorithm. So we can think of this counting algorithm as applying phase estimation to quantum search. The aim of this algorithm is to approximate the total count C. So given an oracle which encodes information about the targets of search, we want to count how many targets of search there are. And that is that value C. So the goal of this algorithm is to approximate the total count C. Now let's have a look at the target of phase estimation. The target of phase estimation for the quantum counting algorithm is the L-qubit unitary operator U, which is composed of the oracle omega and the reflection R. So first we apply the oracle, and then we apply the reflection. That is equivalent to applying this unitary operator, which is the target of phase estimation. And in the yellow box down here, we can see this operator defined. So we have omega and we have R. And if we take the product of these two operators, that's going to give us U. And when we take the product of these operators, that's the same as first applying omega and then applying R. So you can see that in these definitions, we have this notation for quantum states. So let's first have a look at how these quantum states are defined. When you see a plus inside of a ket with a superscript L, that is shorthand notation for a uniform superposition of all of the L-qubit computational basis states. These superscript L's are there to remind us that we're dealing with L-qubit states. We're not dealing with single qubit states. So this summation over here is being used to define a superposition. And G is serving as a label for each of these quantum states. In this sum, G goes from 0 up to 2 to the L minus 1. We can represent these G values in base 10. Alternatively, we can represent them in binary. And when we represent them in binary, we're going to use L-bit strings. How many of these L-bit strings are there? Well, there's actually 2 to the L combinations. So that's why we have 1 over the square root of 2 to the L as the normalization coefficient. So this plus state contains a uniform superposition of all of the computational basis states for an L-qubit system. But these states over here, this one in the middle and this one on the right, they do not contain all of the computational basis states. They only contain a subset. So it's a special subset that occurs over here. In the state that is labeled with capital T, we can call this the target superposition. We have a uniform superposition of all of the target states. Those are the computational basis states which are labeled by the little t's. And the little t's are elements of the set big T. So little t's correspond to the targets of search. That is what we get from the oracle omega. So the oracle omega gives us information about these targets of search. And these little t's are being used to label these states, which are the targets of search. So we can call these the target states. And this uniform superposition of all of the target states is this state over here, with this capital T as the label. And how many states do we have in this superposition? How many target states are there? Well, it's C. C is the total count. That is actually the value that we're trying to find using the quantum counting algorithm. And that's why we have a normalization coefficient of 1 over the square root of C. So this superposition contains only the computational basis states that correspond to target states. And what about the other states? How many of them are there? Well, there's actually 2 to the L minus C states that are not in this superposition. And we can actually put them in a uniform superposition that is going to form a state that is orthogonal to this superposition of target states. So that's why we have a perpendicular sign as the label. So we have a perpendicular sign because this state is orthogonal to the target superposition. And the normalization coefficient over here is 1 over the square root of 2 to the L minus C. So 2 to the L minus C, that's the number of states that are present in this superposition. And you can see H is acting as a label over here, and H consists of all of those L bit strings that are not elements of this set big T. So the little t's are all the elements of big T, and the h's are all the elements that are not in big T. So they're the remaining L bit strings that are not being used to label the targets of search. And you can see that if we add C to 2 to the L minus C, we get the total of 2 to the L. So all of the computational basis states can be found in this state labeled by plus, and only the target states are found in the state labeled by big T, and the remaining states can be found inside of this perpendicular sign state over here. And when we're visualizing the quantum search algorithm, we're going to imagine this target superposition as lying on the vertical axis. And then this orthogonal state is going to lie on the horizontal axis. So we're going to have a two-dimensional plane constructed based on these two states. And this plus state is going to lie somewhere in between the vertical and the horizontal axis. But all of them are going to lie in the same plane. So what we're dealing with here is a 2D plane that's going to help us visualize quantum search, and it's also going to help us visualize what's going on in the counting algorithm. So this over here, this notation for these states is going to be used throughout the rest of this video. And it's also used to define these operators. So at the top over here in this yellow box, we can see the identity operator. And this is the identity operator for an L-qubit system. So that's why we have 2 to the L in the subscript. 2 to the L is the dimension of the Hilbert space. So we're not dealing with a single qubit identity operator. We're dealing with an L-qubit identity operator. That's why we have 2 to the L to specify the dimension of the Hilbert space. And we can express this as the sum of two projectors. And these projectors are formed with these ket-bra pairs. So you can see that over here we have a ket on the left, and then we have a bra on the right. And when you pair a ket and a bra together, and the labels match, that is a projector. So this first term over here on the left, that projects onto the orthogonal subspace. You can think of that as projecting onto the horizontal component if we're visualizing this as a 2D plane. And over here, this projector projects onto the target subspace. So that is constructed from this state, which is the superposition of all of those target states. And you can also think of that as projecting onto the vertical axis. So we have a horizontal projector and a vertical projector. And we have this L in the superscript over here. That's just to remind us that we're not dealing with a single qubit projector. We're dealing with these L qubit states that are being used to construct these Ket-Bra combinations. And in this form, we can actually represent this as a 2x2 matrix. So we're going to use 2x2 matrices because it's very convenient to perform multiplication using 2x2 matrices. And when we multiply omega and r together to get u, it's going to be very convenient to do that using this matrix multiplication. But you need to remember that these are not single qubit operators. So this identity operator does not act on a single qubit. It acts on a quantum state which describes a register containing L qubits. And the dimension of the Hilbert space is 2 to the power of L. So this is the identity operator. And now let's use the identity operator to define the oracle omega. So the oracle omega is the identity operator minus 2 times the target projector. So this projector over here projects onto the vertical axis in our 2D plane. And we have minus 2 times that projector. And if we look at this definition of the identity over here, if we subtract minus 2 times this vertical projector, that's going to get rid of one of these plus copies of the vertical projector, and it's just going to leave us with a minus. So we're going to have plus this horizontal projector minus the vertical projector. And we can express that as a 2x2 matrix as well. And you can see that this matrix looks just like the Pauli Z matrix. But this is not the Pauli Z matrix, because the Pauli Z matrix would be acting on a single qubit state. So that would be a single qubit operator. But this is not a single qubit operator. Instead, it is acting on this state that describes a system containing L qubits. And what does it actually do? What does the oracle do? It marks the target states. So it doesn't do anything to the states that occur in this orthogonal superposition, but it puts a minus sign on all of those target states. So that is actually a way to mark those states. So this oracle is encoding information about the targets of search. When that oracle acts on a state, it actually marks those states if they're in a superposition. So that is actually the action of this oracle. And you can also visualize this, and we will visualize that when we discuss the quantum search algorithm. So this oracle also has a visual interpretation in the 2D plane that we were describing. Now that we've defined the oracle, both in this form and in this matrix representation, let's define that reflection R. So this reflection R can be thought of as a sandwich between these multi-qubit Hadamard gates. And what is in the middle of the sandwich? Well, we have 2 times a projector constructed from this 0 state minus the identity operator. And what we can actually do is we can bring in those multi-qubit Hadamards, and we can act on these 0 states. So these zeros are not zeros for a single qubit, they are zeros for this L qubit system. So you can also think of this as a string of L zeros inside of this ket. And we're forming this Ket-Bra combination, that's allowing us to make a projector. And we have 2 times that projector minus all of these identity states over here. So if we write this identity operator out in full, we can express that in terms of projectors. So that is what's going on in the middle of the sandwich. And then if we bring in this multi-qubit Hadamard gate from the left and also from the right, the identity operator is just going to get sandwiched by 2 Hadamards, and that's not going to do anything, because if you have a Hadamard applied to another Hadamard, the Hadamard squared is just going to be the identity. So this term on the right is unaffected. We still have minus the identity operator. But what about this term on the left? We have turned these zeros into pluses. So that's actually one way you can construct this uniform superposition of all of the L qubit computational basis states. You can initialize all of the qubits in your register in the computational basis state 0. So then you just have L zeros, and then you act with Hadamard gates on all of those qubits, and that allows you to construct this plus state. And we're doing that on this ket over here, and we're also doing that on this bra. So both the ket and the bra are being turned into plus states. And that's what we have over here. And you can also express this in a matrix representation. This is a 2 by 2 matrix. And you can see we have cosine of this angle theta, which we will introduce shortly in this video. So you can see cosine and sine theta occurring over here. So in this yellow box, you can see the definition of these operators. And these ideas are inherited from the quantum search algorithm. And we will define this angle theta later in this video as well. Now that we have gone through these important definitions, let's describe the quantum circuit diagram. The diagram on the left depicts the quantum counting algorithm. On the right, we can see a zoomed in portion of this diagram. First, let's focus on the full diagram on the left. Time flows from top to bottom. At the top of the diagram, labels are provided for each of the qubits. The qubits are represented by vertical black solid lines. Directly below the labels for each of the qubits, you can see the initial quantum state. And in fact, all of the qubits are initialized in the single qubit computational basis state labeled by 0. The qubits are organized into 2 registers. On the left, register X contains mu qubits, and on the right, register Y contains L qubits. The first, second, second last, and last qubits in both registers are shown. These dots in the middle indicate that we have omitted those intermediate qubits. So this works for a general scenario where mu and L are larger than 4. And for practical applications of the quantum counting algorithm, mu and L are both going to be much larger than 4. And if we want to have a look at a special case where either mu or L are smaller than 4, then we're just going to have to remove some of the qubits shown in this diagram. And then we will have an accurate depiction of the algorithm. But for practical applications where mu and L are positive integers larger than 4, this diagram is an accurate depiction of what's going on. So let's have a look at 4 key stages in this algorithm. The green horizontal line shows us a snapshot of the quantum state immediately after initialization. So here we've initialized all of the qubits in the state 0. So we have mu zeros in register X and L zeros in register Y. This is a little bit different to what we had in the quantum order finding algorithm. In the quantum order finding algorithm, this final qubit over here, labeled by Y sub 0, it was initialized in the state 1. That's because we wanted to initialize this register over here, register Y, as a superposition of the eigenstates of the unitary operator, which is the target of phase estimation. And for that unitary operator in order finding, we could initialize a string of L minus 1 zeros followed by a 1. And that state encodes a superposition of the eigenstates of U. But now we're dealing with a different unitary operator. This U that's shown in this diagram is a different unitary operator. In fact, it is a unitary operator that is inherited from the quantum search algorithm. So we have an entirely different U, and it has different eigenstates. So we still want to initialize register Y in a superposition of eigenstates of this target of phase estimation. But how are we going to do that? Well, the way that we're doing that in this diagram is first we're initializing in all zeros, and then we're applying Hadamard gates to all of the qubits. So that brings us to this blue snapshot. And the blue snapshot shows us what happens to the quantum state after we apply Hadamard gates to all of the qubits. So this is also a little different from the quantum order finding algorithm. We did not have Hadamard gates being applied to the qubits in register Y over here. we only had Hadamard gates being applied to the qubits in register X. But in this algorithm, the quantum counting algorithm, all of the qubits get acted on by a Hadamard gate. And that produces the state that is shown in the blue snapshot. So we actually get a superposition of all of the computational basis states. And we're going to mathematically describe that later in this video. So that is what happens over here in this blue state. And this procedure allows us to initialize register Y in the superposition of eigenstates of U. So at this blue stage over here, we actually have a superposition of eigenstates. And now we're ready to apply a sequence of controlled unitary gates. When you see a black circle being placed over a qubit, that marks it as the control qubit in this controlled unitary gate. And the target is this entire register of L qubits. That's register Y. And you can see that U is being raised to a power. You can see 2 to the 0, 2 to the 1, and then we skip over the intermediate gates, and we get to 2 to the mu minus 2, and then 2 to the mu minus 1. Note that these values in the exponents, these powers of 2, they actually match the subscripts in the labels at the top of register X. So you see this mu minus 1, if we follow that qubit all the way down over here, we can see that when it is acting as the control qubit, we have U to the 2 to the power of mu minus 1. So that value matches. And that's not a coincidence. This is a notation that's specifically chosen so that it is convenient, and it illustrates this point. So when we have these vertical dots over here, they're telling us that we're omitting all of those intermediate controlled unitary gates in this sequence. So we're only showing the first, second, second last, and last of these controlled unitary gates. And that brings us to the red snapshot. So the red snapshot describes the quantum state after we apply this sequence of controlled unitary gates. And then we're going to apply the inverse mu qubit quantum Fourier transform to all of the qubits in register X. So that's what this box is telling us over here. This F is for Fourier, because we're applying the Fourier transform, and we also have a dagger on the top, and that's telling us that this is the inverse Fourier transform. And the subscript tells us the dimension of the Hilbert space. We have 2 to the mu, and that is the dimension of the Hilbert space associated with a mu qubit system. So we have mu qubits, and the dimension of the Hilbert space is 2 to the mu. So that specifies this operator over here. After we apply the inverse quantum Fourier transform to register X, we get to this purple snapshot. And the purple snapshot describes the quantum state just before measurement. So then we're going to perform measurements of all of these qubits. And we're not really interested in the results of the measurements of the qubits in register Y, but we are interested in register X. So we want to measure all of those qubits in register X. And that brings us to the zoomed in version of this bottom part of the diagram. So you can see the inverse quantum Fourier transform being applied to register X, and then you can see the purple snapshot and all of these measurement gates. So this symbol over here with a little dial, that is the symbol for a measurement gate. And the input over here is a qubit, and then when we perform the measurement, we're actually going to get a classical bit from that. We're either going to have a 0 or a 1. And here we have labels for all of those bits. And you can see that we have two options. So we have this sequence of bits at the top and another sequence of bits on the bottom. So these two options are the desired measurement outcomes. So that's what we want to aim for. That's what we're trying to measure. And this measurement is going to allow us to work out an approximate value for the total count C. Note that we have a similar notation over here. So the top sequence of bits, they are denoted with this loopy phi. So you can see this loopy phi. And then the bottom sequence of bits, they're denoted with a straight phi. So both of these options are the outcomes that are going to give us the desired answer at the end of the algorithm. So we're going to try and estimate that value of the total count C. And we're going to do that by measuring these sequences of bits. So now you've seen this diagram over here. And it's important to note that this diagram shows us what's going on with the qubits. And it works for the general case where mu and L are positive integers larger than 4. So now what we're going to do is have a look at mathematical descriptions of the quantum state at these 4 key stages. So we're going to have a look at the green snapshot, which tells us what happens after initialization. Then we're going to have a look at the blue snapshot, which tells us what happens after we apply Hadamard gates to each of the qubits. And then we're going to have a look at the red snapshot, which tells us what happens after we apply the sequence of controlled unitary gates. And then finally, we'll have a look at the purple snapshot, which is just before we perform measurements of the qubits. And we're interested in the outcomes of the measurements of all of the qubits in register X. That's actually going to give us the answer that's going to allow us to determine the total count C. And note that the key differences in this diagram, when we compare it to the quantum order finding diagram, are this top right corner over here. So the initialization of register Y is different, and we're applying Hadamard gates over here at the top. So that was not present in the quantum order finding algorithm. So that's a slight difference over here. And another key difference is that the unitary operator U is a different unitary operator. So we have a different target of phase estimation. And that's why we have to have a different initialization procedure to allow us to create a superposition of eigenstates of that target unitary operator. That's the target of phase estimation that we defined. Now let's move over to mathematical descriptions of these snapshots. At the top, the green snapshot shows the quantum state immediately after initialization. The notation on the left emphasizes individual qubit states, whereas the notation on the right is far more condensed. This snapshot matches what we saw at the top of the quantum circuit diagram, where all of the qubits in both registers were initialized in the single qubit computational basis state labeled by 0. And in the blue snapshot, we can see what happens to the quantum state after we apply Hadamard gates to all of those qubits. This notation on the left emphasizes individual qubit states. We can see those individual initial states of single qubits, and we can also see the Hadamard gate being applied to those initial states. And this notation emphasizes those individual qubit states, but we can write this in a far more condensed form. So this notation that is also shown in the blue snapshot is a more condensed format, and it uses that condensed notation for the initial states of these entire registers, and it also has condensed notation for this multi-qubit Hadamard gate. And we have a tensor product in the top over here, and next to the tensor product we have the number of qubits. So on the left we are depicting what's happening in register X, which contains mu qubits. And on the right, we are depicting what's happening in register Y, which contains L qubits. So the format is the same. The only difference is the number of qubits. We have mu qubits in register X and L qubits in register Y. We can write this in an even more condensed format using this plus notation. And we introduced this plus notation earlier in this video. So when we have plus as the label with a superscript at the top, that is telling us that we have a uniform superposition of all of the computational basis states. And we're dealing with multi-qubit systems. When the superscript is mu, we're dealing with mu qubit computational basis states. And when the superscript is L, we're dealing with L qubit computational basis states. Alternatively, we can write this plus notation out in summation notation. So here we have a sum with an index g going from 0 up to 2 to the mu minus 1. G serves as a label for all of the computational basis states. And here we're dealing with mu qubit computational basis states. And we're taking them and we're putting them in a superposition. And this is a uniform superposition. How many states are present in this superposition? Well, it's 2 to the mu. That's the dimension of the Hilbert space of a mu qubit system. And that's why we have this normalization coefficient of 2 to the minus mu on 2. Alternatively, we could rewrite that as 1 over the square root of 2 to the mu, where 2 to the mu is the dimension of the Hilbert space. So we're explicitly writing this out for register X, but for register y, we're choosing to keep it in this condensed form. Why is that the case? Well, what are we actually doing in these first two stages? We have initialization, and then we're creating these superpositions by applying Hadamard gates to all of the qubits. The end goal of this is for register x to have a uniform superposition of all of the computational basis states for a mu qubit system. And we want register y to be prepared in a superposition of the eigenstates of the unitary operator, which is the target of phase estimation. So we're applying the phase estimation procedure. It's very similar to what we did in the quantum order finding algorithm. But there are some subtle differences in these first two steps. In the order finding algorithm, we initialized the final qubit in register y in the state labeled by 1. So we had a string of L-1 zeros followed by a single 1. And that was equivalent to a superposition of the eigenstates of the unitary operator, which was the target of phase estimation. But that was a different unitary operator. That unitary operator was associated with the problem of order finding. Now we're dealing with a unitary operator that is inherited from the quantum search algorithm. And that unitary operator has different eigenstates. And we're actually going to see that the eigenstates can be put in a superposition, and then we can prepare this initialization, and we're going to have a superposition of the eigenstates of U. So at this blue snapshot over here, we have successfully prepared a superposition of the eigenstates of U in register Y. We've just done it in a slightly different way to how it was done in the quantum order finding algorithm. Remember that in the order finding algorithm, we didn't have Hadamard gates being applied over here in register Y. We only applied those Hadamard gates in register X. So that's another notable difference. And we also saw that difference in the quantum circuit diagram. So we could think of that as just putting identity gates on all of the L qubits in register Y. So we didn't need those Hadamards because we had already prepared the superposition of eigenstates in register Y at the beginning in this green snapshot. But now it's not sufficient. Now we're just going to initialize everything in zeros at the beginning, and then we're going to apply Hadamards to all of them. And that's going to give us this format. So now we're ready to move on to the next stage. We're ready to move on to the red snapshot. But let's have a look at what's happening in these boxes. We have a blue box and a red box, and that's going to give us additional information, and it's going to help us see how this red snapshot works. So let's start with the blue box. The blue box gives us some useful information about the state labeled by plus. So that is a uniform superposition of all of the L qubit computational basis states. We can express that as a superposition of the horizontal state and the vertical state. So remember from earlier in this video, we had a horizontal state and a vertical state. The vertical state is a superposition of the target states, and the horizontal state is a superposition of all the remaining states that are not targets. So the targets are encoded in the oracle omega, and all of those target states, they're put in a uniform superposition, and that uniform superposition is used to define this vertical state that is labeled by T. And all of the remaining L qubit computational basis states that are not targets, they are put in this perpendicular state over here. So we have this perpendicular sign. That's because this is orthogonal, and it is a horizontal state. So we're actually interpreting this geometrically as lying in a 2D plane. So we have a vertical state and a horizontal state. And we can think of them as a vertical vector and a horizontal vector. And we can think of this coefficient over here as the horizontal component and the vertical component over here. So the horizontal component is the square root of 1 minus c on 2 to the L, and the vertical component is the square root of c over 2 to the L. C is the total count, it is the cardinality of the set big T, and it is the value that we're trying to approximate with the quantum counting algorithm. So that is what we've got over here. And note that if you take the square of the horizontal component and you add it to the square of the vertical component, you're going to get 1. Now let's redefine these horizontal and vertical components in terms of an angle, and we're going to call that angle theta. cosine of theta on 2 is going to be the horizontal component, and sine of theta on 2, that's going to be the vertical component. And we can think of this as a rotated vector, and it is normalized. Why is it normalized? Well, we can verify that. If we take the square of this cosine, and then we add it to the square of this sine, we're going to get 1. So this is indeed a normalized vector. So that is what's going on with this plus state. And remember, we have plus with a superscript L, and that tells us we're dealing with an L-qubit system. So this quantum state describes an L-qubit system. It's the state of register Y, which is shown on the right in the blue snapshot. And now that we have this useful format, we can think about what this theta actually means. Theta is going to be the value that we're going to estimate in the phase estimation procedure. And because theta is defined in terms of C, we're going to be able to work out what C is. So we're going to be able to approximate C by estimating theta. So this procedure is an indirect way of finding out what C is. We're going to find out C by approximating this value of theta. So sine of theta on 2 is defined as the square root of C over 2 to the L. And you can see that 2 to the L is very important in this definition. It is the dimension of the Hilbert space of this L-qubit system. Now let's do some algebraic manipulation and show that this state labeled by plus is actually a superposition of eigenstates of the unitary operator. In the second line of the blue box, we have some algebraic manipulation. We can see superpositions of superpositions. And then in the third line, we can see some condensed notation. So let's introduce some notation. Plus I and minus I are going to be labels for states. And have a look at this plus I state. It has a superscript L as well, so it is describing an L-qubit system. This plus I state can be written as 2 to the power of minus 1/2 times this superposition of the horizontal state plus I times the vertical state. And if we change this plus sign to a minus sign, we're going to get the definition of this state that is labeled by minus I. So if we have minus I in the label, that corresponds to this superposition. We again have that normalization coefficient, which is included in the definition. So we have 2 to the minus 1/2. And then we have a superposition of the horizontal state minus I times the vertical state. So that is going to be a very useful definition. And it turns out that these states that are labeled by plus I and minus I, they are eigenstates of the target of phase estimation. So let's have a look at why this works out. If we create this superposition of superpositions, we're going to notice that there's going to be cancellation. This term over here, multiplying this I, multiplying the vertical state, is going to cancel with this minus I, multiplying the vertical state. And we're just going to be left with 2 copies of this horizontal state. And that factor of 2 is going to cancel with 2 to the minus 1/2 times 2 to the minus 1/2. And so we'll be left with what we have in the top line. And a very similar procedure can be done for this vertical state. We can prepare a superposition of superpositions, but now we're going to change the coefficients. We're going to put a minus I at the front over here, and then a plus I over here. And that careful choice of coefficients in this superposition allows for cancellations. So we're going to have opposite signs for these horizontal states. Here we're going to have minus I, and then here we're going to have plus I. And they're going to cancel. So there's not going to be any horizontal state. And the minus I and the plus I are going to multiply, and they're going to give plus 1. And that's also going to happen over here. We're going to have I times minus I, which gives plus 1. So we're going to have 2 copies of the vertical state. And the factor of 2 is again going to cancel with 2 to the minus 1/2 times 2 to the minus 1/2. That's because 2 is the same as 2 to the power of 1. So that cancels with these 2 normalization coefficients. And then we're back to what we started with in the top line. So that's just a demonstration of how this top line is equivalent to the second line. And when we go to the third line, we can see we're just using the definition of those eigenstates to write this in a more condensed format. So in this superposition, the coefficients are plus 1 and plus 1. And then this other superposition has the coefficients of minus I and plus I. So that's what we're dealing with over here. And the way that this actually works is what we're doing is we're choosing plus I and minus I because they have a very special property. If you take plus I and you add it to minus I, you're going to get 0, which is the additive identity. And if you take plus I and you multiply it by minus I, you're going to get 1, which is the multiplicative identity. So they're inverses with the operation of addition and the operation of multiplication. So it's a very special relationship. And that's how this actually works. So it's a very convenient choice when we're defining these eigenstates. So that gets us to this final line, and we can also write this in an even more condensed form in terms of complex exponentials. Why is that the case? Well, let's have a look at all the terms that multiply plus I. We can pull out that normalization coefficient of 2 to the minus 1/2, and then we can focus on the trigonometric functions. So we have cosine of theta on 2 minus I times sine of theta on 2. And that produces this e to the minus I theta on 2. So that explains this coefficient. And then for the minus I term, we have cosine of theta on 2 plus I times sine of theta on 2. And that explains this e to the I theta on 2. Notice that the signs are opposite. So when you have a plus sign in the label of the state, you end up with a minus sign in the complex exponential. But the important thing to take away from this blue box is that this is an algebraic proof that the state labeled by plus, which is a uniform superposition of all the L-qubit computational basis states, it is equivalent to a superposition of two eigenstates of the target of phase estimation. And let's see why they are eigenstates. We can see that in the red box. If we apply this unitary operator, which is inherited from the quantum search algorithm, and we apply that to its eigenstates, we can write that as a matrix multiplication problem over here. So this 2 by 2 matrix is a matrix representation of U. And this, you can actually derive this by looking at the definitions in the yellow box that we saw earlier in this video. We had a definition of the oracle, and we also had a definition of the reflection R. And if you take the product of those two matrices, the 2 by 2 matrix associated with R and the 2 by 2 matrix associated with omega, you're going to get this 2 by 2 matrix, which can actually be visualized as a rotation by the angle theta. So we have a rotation by the angle theta, and we're applying that to this eigenstate. And you can see that this column vector over here, it is just the matrix representation of these eigenstates that we defined in the blue box. So you have a horizontal component and then a vertical component. The horizontal component is 1 times 1 over the square root of 2, and then the vertical component is plus or minus I, depending on which eigenstate we're dealing with, times 1 over the square root of 2. So that normalization coefficient is out the front. And when the top entry corresponds to the horizontal component, the bottom entry corresponds to the vertical component. So it's just like we're dealing with a two-dimensional system. But in reality, we're not dealing with a 2D system. We are dealing with an L-qubit system. And that dimension of that Hilbert space is 2 to the L. We are just using this convenient trick to give us these very convenient matrices that are just 2 by 2 matrices. And that's the representation of operators. And then the states, they can just be expressed as these column vectors with 2 entries. And the basis that we're using to construct these matrix representations, it is the basis consisting of this horizontal state and this vertical state. So that's that perpendicular and that target superposition state. And we're treating them as an orthonormal basis, and we are constructing these matrix representations using that orthonormal basis. So now, if we perform this matrix multiplication, we're going to get this column vector. You can see the top entry and the bottom entry. They come from performing matrix multiplication. And note that we have a minus plus sign. That comes from this minus sign over here. And that minus sign flips the sign of plus minus. So when we have a plus, we get a minus, and when we have a minus, we have a plus. And note that the order is incorrect in this bottom entry. So we can't turn this into a complex exponential. We have to factor out a plus or minus I term. And if we factor that out, we're going to have the same format that we have in this top entry. And then we can read that off as e to the minus plus I theta. And this bottom entry, which corresponds to the vertical component, is plus or minus I times that same complex exponential factor. And we can pull that complex exponential factor out of the vector, and then we can identify that as the eigenvalue, multiplying that original eigenstate that we started with. And this notation with plus or minus accounts for both of these eigenstates. So this top line in the red box is actually an eigenvalue equation. And it shows the eigenvalues associated with these eigenstates. And these are the eigenvalues and eigenstates of the target of phase estimation U. Let's also see what happens if we apply U g times to the state plus. So this state plus, that is the same as this state that we started with at the top. So what is the horizontal component? Well, it's cosine of theta on 2, and the vertical component is sine of theta on 2. So that explains this column vector. And what about this 2 by 2 matrix? So each time we apply the unitary operator, it is a rotation by the angle theta. And that's why we have this definition at the top is theta on 2. That is so that the factor of 2 cancels later, and we're just dealing with theta over here. So the value of theta corresponds to something that we can interpret visually as a rotation. So every time we apply that unitary operator u, we're going to be rotating by theta. And if we do that g times, we're going to rotate by the angle g theta. So that's why g theta is the angle that we're rotating by in this rotation matrix. So that's what u to the power of g is over here. And then if we perform matrix multiplication and we use some trigonometric identities, we can simplify that to this form over here. And we can identify this top entry as the horizontal component and this bottom entry as the vertical component. And you can see now we have a superposition of this horizontal state and this vertical state. So we've just changed that superposition. We've changed the angle over here. We started off with just theta on 2, and now the angle is theta times g plus 1/2. So we still have that theta on 2, but now we've added theta times g. So what does that correspond to visually? Well, it's actually a rotation. It's a rotation in this 2D plane. So that's what this red box is telling us. Now we have enough information to have a look at this red snapshot. And the red snapshot describes the quantum state after we apply that sequence of controlled unitary gates. And we can see something very similar to what we saw in the order finding algorithm. We have this big format over here, which allows us to see the sequence of controlled unitary gates. So we first apply the controlled unitary gate on the right, and then we work our way all the way up to the left. So we have this entire sequence of mu controlled unitary gates. And you can see that in the exponents, we have the same bits that are being used to label quantum states over here. So we're writing this out, and we're using bits to label the individual qubit states of all of the mu qubits in register X. And that means we have to have all of these summations over here, and they are summing over bits. So the possible values are 0 or 1. And we can write that in a far more condensed form that is shown on the right. What are all these unitary gates being applied to? Well, they're being applied to the state labeled by plus. So that's just like what we saw in the bottom line of this red box. We have u to the g being applied to this state labeled by plus. And we can also write that in this condensed form. So note that we have two equivalent ways of expressing this. We can either express this in this very explicit notation, which takes into account individual bits, or we can write this in a condensed notation over here. And this explicit notation allows us to individually see the controlled unitary gates that are being applied in this sequence. So now let's focus on this condensed format. We can take that state labeled by plus and we can rewrite it in an equivalent form. So the form that we derived in the blue box, we can substitute that in over here. And if we do that, we can just put that in, and then we can bring in this u to the g in the superposition. So note that this format over here, it's exactly the same format that we saw at the end of the blue box derivation. And all we've done is brought in that u to the power of g, and we're acting on each of the states in the superposition. So u to the g is acting on this eigenstate labeled by plus I, and it's also acting on this eigenstate labeled by minus I. And we know what the action is because we have this eigenvalue equation shown in the red box. So when you apply u to one of these eigenstates, you're going to get this complex exponential that depends on theta. And the sign in that complex exponential is going to be opposite to the sign in the label. So what happens if you do that g times? Well, then you're going to have g theta. So you're going to have g copies of that eigenvalue, and you can bring that in, bring that g inside using exponential laws. And that's going to give us this coefficient over here. So the coefficient of the eigenstate labeled by plus I, that is e to the minus I theta times g plus 1/2. So that 1/2 was originally there. So that's that original coefficient that we had in the superposition. That comes from this blue box derivation over here. And then this extra factor of g has come from applying that unitary operator g times to the eigenstate. So that's why we have g times theta. And we can see a similar process occurring over here in the eigenstate labeled by minus I. The only difference is that we have a different sign in the complex exponential. Now we have a plus sign, and it's opposite to the sign in the label. So notice that we have this theta times g to the plus 1/2 occurring in these complex exponentials. This looks familiar. This is exactly what we saw in the red box. We have this theta times g plus 1/2. So this is something that we can interpret visually on a 2D plane. We can interpret this as rotations in a 2D plane. And that's exactly the same as the visualization of the quantum search algorithm. So that's where this is coming from. So now in this red snapshot, we also want to pay attention to the normalization coefficient. So note that originally we had 2 to the minus mu(1,2) as the normalization coefficient. That was also the normalization coefficient we had in this form in the blue snapshot. But we have introduced an extra 2 to the minus 1/2. That is another normalization coefficient. And that comes from re-expressing this plus state in this superposition. So we have a normalization coefficient that we've added here. And we can pull that out and we can combine that into a single normalization coefficient. So we have 2 to the minus the quantity mu plus 1 all over 2. So that is the normalization coefficient of this state. The next thing that we're going to be doing is applying the mu qubit inverse quantum Fourier transform to register x. And we're going to see how that affects the quantum state. So that's going to take us from the red snapshot to the purple snapshot. The red snapshot shows us the quantum state after we apply the sequence of controlled unitary gates. And the purple snapshot shows us the quantum state after we apply the mu qubit inverse quantum Fourier transform. So compare this format shown in the red snapshot with this format over here shown in the purple snapshot. You can see now there is an inverse quantum Fourier transform acting on register x. Let's consider the definition of the inverse quantum Fourier transform, and let's expand this out. That's going to give us this big summation in the brackets over here. We have a normalization coefficient of 2 to the minus mu(1,2). Then we have a sum over the index k going from 0 up to 2 to the mu minus 1. And in this superposition, the terms have this format. The label of the mu qubit quantum state is k, and the coefficients for each of those states labeled by k have the form e to the minus 2 pi I kg times 2 to the minus mu. So you can see that g is appearing in these coefficients. G was the original label for these states in this superposition, and here we have a sum over g. But now we're introducing this sum over k, and g is playing a role in the coefficients, but k is now serving as the label of these quantum states. So this is describing what's happening to register x on the left. Now let's focus on what's happening to register y on the right. Here we have u to the power of g being applied to the state labeled by plus. Now we saw that combination in the red snapshot, and we did some algebraic manipulation, and we found that it is equivalent to this superposition of eigenstates. And we can write that superposition over here. Note that we are including this normalization coefficient of 2 to the minus 1/2. In this final form in the red snapshot, we factored that out and we merged that with the other normalization coefficient to produce a single normalization coefficient. Now we're explicitly writing this 2 to the minus 1/2 over here. So what is present in this superposition? Well, we have two eigenstates. We have the eigenstate labeled by plus I and the eigenstate labeled by minus I. These are the eigenstates of u, which is the target of phase estimation. And here are the coefficients that we're dealing with over here. And these coefficients result from the application of u g times. So we apply u g times to the state plus, and it gives us this superposition with these specific coefficients. Now that we have these definitions expanded out, we're going to perform some algebraic manipulation. And that algebraic manipulation is going to have a lot of steps, but it's going to allow us to turn this expression into a format that is much more understandable. Because in this format, we can't really see what's going on. What are we actually going to measure? This purple snapshot shows us the quantum state before measurement, and we want to know what the probabilities are for different outcomes of measurement. And you can't really clearly see that in this format. So that's why we're going to do a sequence of algebraic manipulations. So first, we're going to do some reshuffling. We're going to move this sum over k all the way out to the left. And then we're going to have these big brackets, and they're going to include everything over here. So everything in these brackets is going to correspond to a single value of k. And then we're going to sum over k, and it's going to go from k equals 0 up to k equals 2 to the mu minus 1. So that's a total of 2 to the mu terms. And they're all being described by this format in these big brackets over here. And in these brackets, we have two terms. We have this term on the left, and we have this term on the right. And you can see that in both of these terms, we have sums over g. So we've taken that sum over g, and we've moved it in to this part over here. And we're summing over g in this part, and we're also summing over g in this part. And that's going to allow us to define some concise coefficients in this superposition. And we can also see normalization coefficients that are the result of a merger of three different terms. So we have 2 to the minus mu on 2, and then another copy of 2 to the minus mu on 2, and then we have 2 to the minus 1/2. If we smush all of those normalization coefficients together, we're going to have this 2 to the minus 2 mu plus 1 all divided by 2. So that normalization coefficient comes from combining those three normalization coefficients. And you can see that the term on the left corresponds to this eigenstate plus I, and the term on the right corresponds to the eigenstate minus I. And what is going on in these labels for register x? So we no longer just have k. We've actually shifted these labels. So here we've subtracted big phi, mod 2 to the mu, and here we've added big phi, mod 2 to the mu. So we're doing shifts modulo 2 to the mu. We're doing modular arithmetic inside of this label. And the value that's present in this label is also present in these complex exponentials over here. Where have these complex exponentials come from? You can see we have a complex exponential raised to the power of g. Well, we can use exponential laws and we can bring that g back in. And then we can see that all the terms that have g in them, they are appearing over here. So when we had theta times g, that's also showing up over here. We have theta and we're multiplying it by g if we use exponential laws. And we also had kg in this term that originated from the inverse quantum Fourier transform. So that's this k over here, and it's being multiplied by 2 to the minus mu. So all we're doing is we're taking those terms that have g, and we are putting them together into one complex exponential, and then we're using exponential laws to factor that g out and to turn it into an exponent. So that's what's happened in this term, and that's what's happened in this term. And now we can sum over g. So we have a sum over g over here and a sum over g over here. What about the parts of these complex exponentials that do not depend on g? You can see in this superposition, we have e to the minus I theta times g plus 1/2. So that 1/2 does not depend on g. So we can actually remove that, and we can take that out, because that's not going to be involved in this summation. So that explains this e to the minus I theta on 2. And that's present in the left term, and in the right term, we have the opposite sign. We have the complex conjugate. We have e to the I theta on 2, and that comes from this factor of 1/2 present over here. So if we multiply these complex exponentials that come from the inverse quantum Fourier transform, and we distribute them over, and we multiply them, and then we're going to have combinations of complex exponentials, and then we can group all the parts that depend on g, and then we can get rid of the parts that don't depend on g. And we can factor those parts outside of the summation over g. So that gets us to this format over here. So we have this complex exponential that does not depend on g, then we have a normalization coefficient, then we have a sum over g, and then we have this complex exponential raised to the power of g. And all of this is a coefficient of these states over here. And pay close attention to what's happening with the signs in these complex exponentials. When you see a minus theta that corresponds to a minus phi shift. And when you see a plus theta over here, that corresponds to a plus phi shift. So that's not a coincidence. That is purposefully chosen over here. And let's have a look at what we have to divide this theta by. So because we have this format where we have 2 pi I over here, we have to divide theta by a factor of 2 pi. So that explains this 2 pi in the brackets here and this 2 pi in the brackets over here. So that's what we're dealing with inside of this complex exponential. Note that inside of this complex exponential, we can actually add and subtract 1. So imagine adding 1 over here in front of this minus theta. That's the same as adding 2 to the mu inside of this little bracket over here. So then we would have k plus 2 to the mu minus phi. And that 2 to the mu would cancel with 2 to the minus mu, and that would give us a 1. And then because we have a minus sign over here, we'll be able to cancel out, and we would have a minus 1. So that 1 would cancel with a minus 1. Why am I going through that specific algebraic example? Well, it's because have a look at what's going on in this purple box. In this purple box, we have these 2 different approximators for theta. Let's focus on the one in the top first. Theta divided by 2 pi can be approximated by big phi times 2 to the minus mu. And here we have a binary fraction representation, and we also have summation notation, which can help us elucidate how this big phi is defined. And on the left, we can also see how this is shown as a quantum state. So if big phi is the label for a quantum state, we can express it in this format over here, where we have mu single qubit states. And each of the labels for those single qubit states are bits. And these are actually the bits that we want to measure. And that's what's happening in this top diagram over here. So theta on 2 pi is approximated by big phi times 2 to the minus mu. And if we look in the bottom, we have an analogous expression. And now over here we have 1 minus theta on 2 pi. And that is being approximated by the quantity 2 to the mu minus big phi all times 2 to the minus mu. And you can see that if you distribute this 2 to the minus mu, you're going to get a 1 over here. And you can cancel the 1s of both sides over here. And that's going to show you that you still have the same approximation. So this big phi up to a factor of 2 to the minus mu is approximating this quantity of theta over 2 pi. And why are we including this value of 2 to the mu minus big phi? Well, it's because this is one of the options that we might actually measure. So if we look over here on the left, we can see this quantum state that is labeled by 2 to the mu minus big phi. And we have an alternative notation for the bits that are serving as labels. And you can see we're using a straight phi instead of a loopy phi. So that's just like in the quantum circuit diagram, where we had those 2 options of bit sequences that we want to measure. So we might measure this loopy phi bit sequence, which corresponds to big phi, or we might measure this straight phi bit sequence, which corresponds to the state labeled by 2 to the mu minus big phi. Either one of these options are going to allow us to determine an approximate value for C, which is the total count. So have a look at this bottom line in the purple box. C is defined as 2 to the L times sine squared of theta on 2. So remember when we were looking at the definition of theta, and we were introducing it, and we were trying to describe it as a visually intuitive interpretation of the quantum search algorithm. We saw that the vertical component was sine of theta on 2. And sine of theta on 2 is equivalent to the square root of c on 2 to the L. And if we take the square of both sides and we multiply both sides by 2 to the L, we're going to get this exact expression. So this is an exact relationship that links together the total count c with the angle theta. And what we're doing with phase estimation is we're approximating the value of theta. So now let's have a look at these approximate formulas over here. So we still have 2 to the L times sine squared, but inside of these sine squared functions, we have these values emerging. And where are these values coming from? Well, if we look back into this purple box, you can see that theta over 2 pi is approximated by big phi times 2 to the minus mu. So this is an approximate relationship. That means we can substitute this value of big phi times 2 to the minus mu in place of this value of theta on 2 pi. So let's do that. If we do that, then we can manipulate this expression over here, and that's going to give us pi times 2 to the minus mu times big phi inside of this sine function. So if you divide this theta on 2 by pi, and then if you also multiply by this factor of 2 to the mu, you're actually going to get an expression in terms of big phi. But I think in this format, it is easier to think of it as theta on 2 is approximated by the quantity pi times 2 to the minus mu times big phi. So that's an approximation for that half angle theta on 2. And then what we can also see is that if we substitute this value in place of this value, we're going to get the same value when we put it into the sine squared function. Why is that the case? Well, if you have 2 to the mu minus phi in place of phi, this 2 to the mu is going to be multiplied by this 2 to the minus mu. They're going to cancel and give 1, and that's just going to leave a factor of pi. So instead of having the original angle, we're going to have pi minus the original angle. And that's equivalent when we put it inside of the sine squared function. So those two inputs are going to give the same output when we insert it inside of this sine squared function. So either one of these options are going to give us a decent approximation of the total count C. That's because even though we have these two different values, when we put them inside of the sine squared function, we're going to have the same output. And that is what this purple box tells us. It gives us some insight into the values that we want to measure. And that explains why we're doing these shifts. That explains why on the right term over here, we're shifting by plus phi mod 2 to the mu, and over here we're shifting by minus phi mod 2 to the mu. And you can see that that shift is also present inside of these complex exponentials. Because if we shift the label, we also have to apply that shift to this term inside of the complex exponential, because that's a coefficient that is associated with that specific state that is labeled with k minus phi mod 2 to the mu. And you can see that we are summing over all of the values of k over here. So now let's introduce some notation that is shown in the green box. We have notation for these coefficients. So we have alpha sub plus or minus k. And you can see that this takes into account both options over here. We have this coefficient on the left and this coefficient on the right. Both of these options are taken care of by this notation. So we're going to have alpha minus k on the left and alpha plus k on the right. And another way we can express this is in this format over here. So this is another way of expressing this big sum. And you can derive that using the geometric series. So that we're actually going to prove that in a later video. But it's just important to have this definition present over here, because it allows us to express these coefficients in a far more convenient way. So instead of having this massive sum with normalization coefficients and a complex exponential, we just have a single value, alpha sub minus k. And it is multiplying this left term, and then this right term is multiplied by alpha plus k. And you can see that minus k corresponds to this minus phi shift, and this plus k corresponds to this plus phi shift. And that sign is opposite the sign that is present in the label for these eigenstates. Here we have plus I, and here we have minus I. So now we have this superposition and these two options over here, and we have to sum that over all of the options of k. So what are these probability amplitudes going to be? Well, we're going to do some analysis, and we're going to show that this equation over here is approximately equal to this expression in the bottom right. So you can see an approximately equal to sign over here. So we're just going to have 2 to the minus 1/2 as the coefficients of both of these terms. So we're going to have a 50% probability of measuring this in register X, and we're going to have a 50% probability of measuring this in register X. And we're not interested in the results of measuring register Y. We're only interested in the results of measuring register X, because that's going to give us the values of 2 to the mu minus phi or phi by itself. And if we measure 2 to the mu minus phi, or if we measure phi, we're going to have an accurate representation over here, because this total count C does not depend on which outcome we get. So as long as we get one of these two outcomes, we can just put them inside of this sine squared function, and that's going to give us the same output over here. And that is an approximation for the total count C. So what is this actually going to look like when we measure it? Well, when we measure it, we're going to see this notation over here is very useful, because this notation shows us what is actually going on in each of the qubit states. So in this top option over here, we're going to have the loopy-phi's, and they're going to be all the bits that we measure. And we saw that at the bottom of the quantum circuit diagram. But in the other option, we're going to have this straight phi, and it's going to show us all the bits that we're going to measure. And these bits are labels for computational basis states. So when we say that we get a bit after we perform a measurement, what we mean is we measure in the Pauli Z eigenbasis, and then we actually get one of those computational basis states. So we figure out that the system was in one of those computational basis states upon measurement. And from that, we can say we either got a 0 or we got a 1. Those are the two values that we can interpret that. And those are the labels for those states. And that is going to give us a sequence of bits. So we're going to have two possible sequences of bits, and either one of those options are going to give us this total count C. Now, why is this in the green box up here? Well, it's because it's going to help us determine the initialization procedure. So this green box will help us figure out the value of mu, because L is going to be determined by the search algorithm. It's going to be determined by the conditions that we saw when we were doing the definitions towards the beginning of this video. But what about mu? Mu is going to be chosen depending on our tolerance for error. So how good is this approximation going to be? That's going to be determined by mu. And we're going to see that in further analysis of the quantum counting algorithm.